All right, so some stuff that we can remember here. So metallic tips, they enable this field enhancement from visible range up to the terahertz range. So the field confinement is several times smaller than the wavelength. So this is something really impressive that those tips provide. And when we remember the Kaiman's talk, it's all about focusing, right? So that's an important message to take. And now the near field, I really like this figure from Rainer as well. So I just, I made my drawing of the same figure just for you to, to see that, yeah. So near field reflection in this quasi-electrostatic limit actually carries the complex information of your samples, complex dielectrics of your sample. Higher harmonics demodulation provides background suppression and also ensures that you have a nanoscale resolution. So these are all things that we know already. So now let's put this in an interferometer, but an interferometer in the way I showed you, right? Not a pseudo-heterodyne, but a classical interferometer. So I just put a scheme here, all the names that we gave before. But why do we use an asymmetric interferometer? This is one question, right? So if we take the classical microscope interferometer, that's we've seen many times already in this talk, right? Basically, we divide the two beams, and they come back to the beam splitter, and they go to the detector, and we interfere these two beams. That's basically what we do. And if we have a broadband source, we have a broadband interferogram. All right, so if we put the sample here, and that's what we do in the classical FTIR experiment, you measure, let's say, a reference interferogram and spectrum, and then you put your sample there. When you put your sample there, of course, the sample is interacting with the two beams. So it means that both signals that are coming here, they carry the information from the sample, right? So it's impossible to decode these two, decode this phase information from this, in this kind of experiment. So now, if we go to a different configuration where we have still far field, right? When we have the sample in one of the arms of this interferometer, now the sample information or the sample absorption is just in just one of these fields that are coming here. But of course, the detector is still mixing everything. There's no way to, let's say, take this information out with this kind of setup. But one message here is important, is that if we think about this arm here as the SNOM arm, right? That's the place we have the sample information. So the asymmetric microsome interferometer that we use in SNOM is more or less like this. You have, it's now like this, right? And the point here is that a asymmetric interferometer, let's say, gives access to this phase information. It doesn't mean that it's enough to measure the phase, right? But it's a requirement. So when you add the time signature in the tip and stuff, you can actually get this phase information, right? Now talking about SNOM and nano-FTIR. So this is consistent with Rainer showed in his talk. When you look at the signal at the detector, when we have this configuration, right? So it's just an example, just using a far field example for you to see that an asymmetric interferometer is really required. All right, so now this is really reviewing what we saw before. So if we take a situation that we don't have any interference arm here, we are just like taking the signal from the tip, this is scattering from the tip, and as Rainer presented, we have two kind of signals here. One is the near field, and the other one is this confocal background, right? So we can write there that we have the scattering is the field scattered is a scattering coefficient times the incident fields. Okay, so you can write this coefficient as this summation of coefficients, near field and background, and you have this coefficient as complex quantities. So this is related to the amplitude and phase of the near field and the background, and you actually can write down this. That's the same expression that Rainer showed before putting the interferometer. So when you use the dynamics of the tip, you have this signal with dependence of the tip height, and having that and knowing that the signal is, let's say, the near field signal is nonlinear, you can actually separate those two signals. But let's say, all things considered at this point, tapping AFM introduced this time signature to the near field optical signal. The nonlinear Z dependence of the near field allows higher harmonics demodulation, and that's this kind of signal you have at the detector. But at this point, higher harmonics demodulation is not enough to actually have a fully, let's say, suppression of the background, because you still have mixing of the near field and the background here, as you can see here. All right, so interferometry is still demanded. So I'm repeating this just to show you that when we introduce this to this stage to a nano-FTIR interferometer, we have the same rules for the near field interaction and this definition of the fields that come from the tip sample stage. All right, so now when we put an interference arm, we actually add this reference field here, and then the signal at the detector now has also a dependence with this reference field here. All right, if we consider, let's say, the amplitude of the near field, that's, let's say, bigger or higher than it's larger than the background amplitude here, for the case that we go for the harmonics of this tip, we can actually write down this expression like this. And if we define here, now if we have this reference being here stronger than the background that we have from the confocal volume from the tip stage, we can actually rule this part here, and now we have a signal that is not anymore, let's say, mixed with the background. It's actually a signal that depends on the reference, the phase of the reference, and the phase of the near field. So interferometric detection enables this complete background suppression when combined with higher harmonics demodulation. Near field amplitude and phase are now accessible if you synchronize your tip with the measurement, and the reference arm allows demultiplexing the broadband response of the source in this case. So that's, I would say that that's the inclusion of the known concept into the, let's say, asymmetric Michelson interferometer that I showed you before. Okay, some practical aspects. So interferogram acquisition. So why we have an asymmetric interferogram? That's one question, right? So let's take this condition here that we have the moving mirror in 3 different positions here. One is the position that we have, the white light position, right? We see the center burst of the interferogram. Here, it's a little bit before that, and here is a little bit after that, right? So in this first situation here, if we think about different pulses that travel in these two arms, in one arm, I have the reference, in the reference arm here, I have this reference pulse, right? And in the, let's call near field arm, or tip sample arm, we have this tip sample pulse, right? Tip arm, let's say. And here, of course, I put already some, let's say, retardation between them, because I know that when they interact, one of them interact with the sample, and then we have a phase delay related to the interaction with the sample. When you do that, you actually have, in this case here, a perfect overlapping between those two, and we have this white light position. When you have a situation that you are a little bit behind here, it means that this reference arm is longer than the tip sample arm. In this case, the reference pulse is even more delayed with respect to the tip pulse. So it means that when this pulse interacts with the sample, it delays a little bit, and they become not perfectly aligned, but it's still a good interference between them. All right, that's one condition. If we go exactly the same value to the other side, let's say that we moved here minus delta, and if we go plus delta here after the white light position, we can have this situation here, which is the situation where this arm here is shorter than this arm here. In this case, we invert this condition here. So this reference pulse is actually ahead, the tip sample pulse. When we interact with the sample, we delay a little bit more. So we split them even more apart, right? So it means that for the same distance around the white light position from one side and other side, we produce totally different, let's say, interference between those two pulses. And of course, this one is weaker because I have just the tails of this pulse interacting. In that sense, that means that in this condition here, the interference decays very fast. And the other one, I can probe the two pulses perfectly. But this one, I always miss, let's say, the retardation of the sample. So this is an example of a synchrotron nano-FTIR spectrum on silicon dioxide. And you can see all these SPP oscillations here in just one side. And the other one is very sharp. Looks like the reference, right, at the silicon on this side. So it means that because of this geometry here, we have most of the sample's response, not all the sample response, but a good part, most of the information is at one side. So we can take advantage on this. So we can scan just more or less half of the interferometer. We can save some time with that, right? I took this nice slide from Iban thesis. So, of course, we need to adjust the apodization function here. In one side is longer than the other, but we still need some apodization here just to avoid those crazy oscillations when you have a boxcar function, right? And yeah, so I think that's something that explains how these interferograms become asymmetric. All right, so now moving to normalization. So this is why we need that, right? That's the question. And we need to remove or to compensate many things in this experiment. So as I showed you before, instrumental line shape is one thing that is related to this apodization function. This is something that we need to, let's say, take into account. The detector spectral responsivity is also not linear, so you need to take this into account. Environment, so you could see already several overtones of the water vapor and also CO2, many things, substrate influence. So how we do it, right? So basically we take a spectrum or an interferogram from a flat response material like silicon, for example, and we record that, and then we take the measurement on the sample. So we have these two complex interferograms, right? We Fourier transform them, and we have now two complex spectra. And in the end, what we need to do, as Martin was pointing out, we need to do a complex division here, right? When we do that, we divide the amplitudes, and we subtract the phase. So now we have a phase contrast with respect to the substrate. That's an important point that was stressed yesterday, right? We need, to talk about phase, there is no sense in talking about just phase, but we need to talk about phase shifts, phase contrasts, phase delays. It's always related to something. So here is the way we do this normalization in the nano-FTIR. So I have an example here. It's an old data from the old machine, but I think it's a good data to show. So this is just a measurement on gold. So what you see here is 40 interferograms on gold, and this is amplitude, this is phase, and this is real part and imaginary part. If we average them, you have this kind of signal. And if we Fourier transform this, we have the amplitude, the phase spectrum, and we have also the real part and imaginary part of this spectrum. All right, so we can do the same for the PMMA sample, for example, right? You can see here that the amplitude drops. Of course, it's a weaker scatterer compared to gold. That's a sort of mirror. And we have also the phase spectra here. So phase wrapped here, but don't worry about that right now. So as I showed you before, we need to normalize this to actually have a spectrum, and we divide the signal of the sample by the signal or the complex response of the substrate. That's the kind of spectrum we get. So that's the amplitude, and that's the phase spectrum, normalized, right? So, of course, we can do more things here to make this spectra more, let's say, presentable or more, like, let's say, yeah, so we can refine them. Tobias is going to present this afterwards, how to actually handle this kind of spectrum. How do you do, let's say, baseline correction, some smoothing, and these sort of things, right? But here I just did from in the amplitude, it's just a simple smoothing, and here I did a phase unwrapping, a baseline correction, and the same smoothing, and you can see nicely the C double band here and the other bands from PMMA, right? So there is no much magic here. You really need to divide those signals and then do some post-processing here. Still simple. I mean, the only one that's actually, let's say, changing the data here is the smoothing, and this should be done with, let's say, with careful, right? You never want to kill a peak or introduce extra peaks, right? All right, so talking about normalization, so there is another important point to remember is that we have a piezo stage here usually, and we measure for many hours. right? So it means that we can actually have some drifts between the time that you take the reference and the time that you measure your sample, right? And if you have a drift here, it means that the encoder doesn't know about these drifts, right? The encoder still thinks that the mirror is at the first position that you put, and so on. So you can have this sort of drifts or offsets in the interferogram, right? And when you have that, you actually produce you add some phase to the spectrum. It means that you add some slope in this baseline of the phase spectrum. So there is a way to deal with this. So I think Tobias is going to show also how to baseline this kind of spectra. And, but it's just for you to remember that this is something that we need to pay attention, mostly when we have these long experiments. One thing to do is to avoid very long experiments. Then you can control more this. You take, let's say, several, let's say, quick experiments, quick spectra, and you can add those in the end, just knowing what's happening with each one. This could be something to do. Okay, so I have some final remarks here. So something also very important to remember is that this reading of the amplitude and phase has a tremendous impact in the, let's say, in the kind of information you can get there. As we're talking about nano-FTIR, we always compare to FTIR. So I'm in a synchrotron. So we have a community that comes, they know how to do an FTIR experiment, and they sort of want to see same things at the nanoscale, but of course they need to understand this data. So here, this work here is a very good work that shows the, let's say, the correspondence between the nano-FTIR absorbance and the far-field FTIR absorbance. And this is really important for people to use, at least for these weak scatterers, to use this as a real tool for spectroscopy. You can really, if you take the nano-FTIR absorbance, I know that there is some discussions between what to use phase or use the imaginary part, of course, but I mean, if you take the imaginary part, it's, let's say, in most of the case, for this kind of, let's say, organic samples, weak scatterers, you can have a good correspondence between the nano-FTIR absorbance and the classical FTIR absorbance, right? And this was important, as I mentioned it, when this paper came out, this was a real attractive thing for the classical FTIR community to actually enter this nanoscale field. All right, so this is the last slide before my conclusion. So something to remember also about this technique. So when we compare the classical experiment, this is just a PMMA film, 25 nanometers on gold, and we just put this on an ATR crystal, and that's a beautiful spectrum we get, right? So users, they like that. It's a beautiful spectrum. You see all the bands you want. Crazy high signal-to-noise ratio. Good. Right, so when you go to the nanoscale and you see a spectrum like this is really amazing, because we are talking about, if you compare the two experiments, we are talking about a comparison between volumes that's more or less 10 to the 10. So it's a very small number of molecules. This is, even if you have, you know, such a high signal-to-noise ratio, if you go scaling this linearly, you never get a data like this. So it means that you need really the field enhancement at the tip to actually be able to access this kind of information. So this is a message that I bring to the users every time they want to they are a little upset that the spectrum doesn't look good at the nanoscale, but it is good, right? So I have a list of key points here. I think as it's recording, I will not go through them, right? And here, some books that I used. Here, some references that I used to produce this presentation. And I want to thank the organizers again and you for the attention.
Thank you. Thank you very much. Thanks, Raul. We still have time to take questions, please. Let me ask the first question. Back to exactly Fourier transformation, we are overlapping two waves. Mm-hmm. You never talked about coherence because interference term has also this coherence in it. Can you comment on that?
Yeah, so the synchrotrons, we are talking about like time coherence, right? It's not transverse coherence. No. So at this new synchrotrons, and for the infrared range, we are coherent in both ways. So we are transverse coherent and also longitudinally coherent. And this is just because the electron bunches, they are too close to each other, and it's coherent. But yeah, so as much as I can say is that you must keep the phase relation between all these pulses that are coming to the detector. I don't know. What do you want me to say? I don't know.
Well, the interference term contains not only the two fields, E1 and E2, which is a cross correlation that you do, mm-hmm. But it also contains a term, the cosine has the coherence term gamma, let's say, right. Which is exactly gamma 1, 2. So if you go more into detail, possibly that we can even analyze this more subtlety to that.
I see.
Yeah.
All right.
Maybe it fits now to ask a question. You have two broadband sources, and I guess you have both of them. One of the thermal source, the hot wire emitter, the Planck emitter, and your source. Mm-hmm. Now, can you compare the spectra and the noise which you get from these both sources, both in the normal FTIR? Do you have curves of that? And then in the nano-FTIR, of course.
All right. So it's a funny story that if we talk about far field and a classical experiment, this is an experiment that's flux hungry, right? You need power. You need as much power you can crossing your sample in this big beam, right? That's the classical transmission. Right. So with the synchrotron, the total power of the beam is lower. It's a big machine, but it's lower than the. Yeah.
It's not the power I'm asking, but it's the quality of spectra. The quality of spectra.
Yeah, I was.
And so the signal to noise. I mean, can you plot the best spectra you get? Can you plot them for both sources on one graph? That's my question.
Yeah, I don't have them here, but in the end, what I was saying is that the noise is very close to the noise to the kind of noise you have in a broadband in a thermal source. So it's a stochastic noise that decreases with the square root of n, right? But the power, we are talking about signal to noise ratio. So the power sort of defines the signal-to-noise ratio. In that case, at the coherence, yes. The signal-to-noise ratio in that experiment, the synchrotron is maybe 10 times lower in that far-field experiment, right? But when you go to the nano-FTIR, and now comes the advantage of the synchrotron, which is a bright source. It means that the flux divided by the area of the source is way higher than a thermal source that's a big source that has a big power, but the power density, the power spectral density is low. So in that case, the signal-to-noise ratio at the tip is maybe 100 times better than a thermal source.
So your near-field spectra are 100 times more reliable than 100 times better?
Yeah,
Repeat. Okay.
yeah, that's a normal number. But it's all about this advantage of the size of the source and
I would just make a comment and a request to NeoSpec. It's quite of practical interest. So maybe you can show the slide where you show the spectra, the reference spectra, and the sample spectrum.
yeah.
Because that is something that recently came up in my group in the discussion, and there's something that don't want to forget it. So you have two phase spectra here, and you see that in the phase you don't recognize anything, right?
Yeah.
So, but if you divide, then this falls off, and these are all kind of phase ramps. And these phase ramps actually are an imaging effect. They come because if you show the interferogram, the white light position is in the middle of this window, and the origin of this window is to the left side, right? So the interferogram is in the center. If NeoSpec would directly in the software put the center at the white light position, then all these phase ramps would vanish, and you would see, even without any normalization, would see the phase spectrum. So it's a very simple thing, and you would see online, without normalizing, immediately the response of the sample. So, NeoSpec guys, where are they? So that is something that, because it's really powerful, and we had a lot of discussions lately in the group, because it's in principle unneeded to look at this data that way. So just
Yeah, this is actually a really good idea. I mean, now when I have users that they just want to measure nano-FTIR absorbance, I will never do reference spectrum anymore. I would just shift the interferogram to 0, and that's it, right? That's what you're talking about.
Cool. Okay, let's thank Raul once again. Thank you very much.